The universe is full of wonders, each more fascinating than the last. Among these celestial marvels, neutron stars stand out as some of the most intriguing and mysterious objects in the cosmos. Neutron stars are the remnants of massive stars that have ended their life cycles in spectacular supernova explosions. These remnants are incredibly dense, with a mass greater than that of our Sun, compressed into a sphere just a few kilometers in diameter. These objects are not only dense but also spin at astonishing speeds, sometimes rotating hundreds of times per second. This rapid rotation, combined with their intense gravitational fields, makes neutron stars truly extraordinary. When a massive star explodes in a supernova, its core collapses under gravity, forming a neutron star. This process is one of the most violent and energetic events in the universe. Neutron stars offer a glimpse into the extreme physics at play in our cosmos. Their intense magnetic fields and rapid rotations create beams of radiation that sweep across space like cosmic lighthouses. These beams of radiation, known as pulsars, can be detected by astronomers here on Earth. Studying them helps us understand the behavior of matter under extreme conditions. Neutron stars challenge our understanding of the universe. Their immense gravitational pull is so strong that it warps the very fabric of space-time around them. Their properties are so extreme that they seem almost unimaginable. The magnetic fields of neutron stars are billions of times stronger than any magnetic field we can create on Earth. Yet, these objects are very real and provide valuable insights into the nature of matter and gravity. By studying neutron stars, we can learn about the fundamental forces that govern the universe. Neutron stars emit intense radiation, which can be detected across vast cosmic distances. This radiation provides a wealth of information about the conditions within these stars. This radiation is detectable across vast cosmic distances, allowing astronomers to study neutron stars from millions of light years away. By studying this radiation, astronomers can learn about the extreme conditions that exist within these objects. This research helps us understand the limits of physical laws and the behavior of matter at its most extreme. The study of neutron stars helps us to understand the life cycle of stars and the fundamental forces of the universe. From their violent births in supernovae to their role as cosmic beacons, neutron stars are key to unlocking the mysteries of the cosmos. Stars much more massive than our Sun end their lives in spectacular explosions called supernovae. These cosmic events are not just the end of a star's life, but also the beginning of something new and extraordinary. These explosions are among the most energetic events in the universe, releasing more energy in a few seconds than our Sun will emit in its entire lifetime. They briefly outshine entire galaxies, casting a brilliant light that can be seen across vast distances in space. A supernova explosion marks the death of a massive star and the birth of a neutron star. This transformation is a dramatic and violent process, reshaping the very fabric of the star. When a massive star runs out of fuel, it can no longer support itself against its own gravity. The balance that once held the star together is lost, leading to a catastrophic collapse. The core collapses rapidly, in a fraction of a second, reaching incredibly high densities and temperatures. This collapse compresses the core's protons and electrons, forcing them to combine into neutrons. This process creates a dense, neutron-rich core. This process releases an immense amount of energy, powering the supernova explosion. The energy released is so vast that it can outshine entire galaxies for a brief period. The outer layers of the star are blasted into space, creating shock waves that travel through the surrounding interstellar medium. This material forms a beautiful expanding cloud of gas and dust called a supernova remnant. These remnants can be observed for thousands of years, providing clues about the star's life and death. At the center of this remnant lies the newly formed neutron star. This neutron star is incredibly dense, with a mass greater than that of the Sun but compressed into a sphere only about 20 kilometers in diameter. This dense object contains the remnants of the star's core, now transformed into a neutron-rich state. Neutron stars are among the most extreme objects in the universe, with gravitational fields so strong that they warp space and time around them. Neutron stars are incredibly dense. They pack the mass of 1.5 suns into a sphere only about 12 miles across. To put that in perspective, a teaspoonful of neutron star material would weigh billions of tons on Earth. This extreme density is a result of the neutron star's formation process. When the star's core collapses during a supernova, the protons and electrons in the atoms are squeezed together, leaving mostly neutrons. These neutrons are packed incredibly tightly, resulting in the immense density observed. The density of a neutron star is so high that it is difficult to comprehend. It is unlike anything we experience on Earth. This extreme density also creates incredibly strong gravitational fields around neutron stars, warping the fabric of space-time. Some neutron stars, called pulsars, emit beams of radiation that sweep across space like cosmic lighthouses. As a pulsar rotates, its beams of radiation sweep past Earth at regular intervals. We detect this radiation as pulses, hence the name pulsar. These pulses are incredibly regular, acting like cosmic clocks. The regularity of these pulses is due to the neutron star's rapid and stable rotation. Pulsars can rotate hundreds of times per second, making them some of the most precise timekeepers in the universe. The discovery of pulsars in the 1960s was a major astronomical breakthrough. It provided the first concrete evidence for the existence of neutron stars. Pulsars have since become invaluable tools for studying a wide range of astrophysical phenomena. Section 5. Magnetic powerhouses. The extraordinary magnetism of neutron stars. Neutron stars possess incredibly strong magnetic fields. These fields are trillions of times stronger than Earth's magnetic field. The strength of these fields is a result of the conservation of magnetic flux during the star's core collapse. These powerful magnetic fields play a crucial role in the emission of radiation from neutron stars. They channel charged particles, accelerating them to incredibly high energies. These particles then emit radiation across the electromagnetic spectrum. The study of neutron star magnetic fields provides insights into the physics of extreme magnetic fields. These insights are difficult to obtain in laboratories on Earth. Understanding these magnetic fields helps us to understand the behavior of matter under extreme conditions. Collapsing star. Similarly, as a star's core collapses, its rotation rate increases dramatically. This rapid spin can lead to the formation of a neutron star with incredibly high rotational speeds. This rapid rotation contributes to the regularity of pulsar signals and the stability of their magnetic fields. Pulsars emit beams of radiation that sweep across the sky, and their precise timing makes them valuable tools for astronomers. The study of neutron star spin rates helps astronomers understand the dynamics of stellar evolution. By observing these spin rates, scientists can gain insights into the life cycles of stars and the extreme conditions that lead to the formation of neutron stars. These spin rates provide crucial clues about the processes that occur during supernova explosions and the formation of these extreme objects. Understanding these processes helps us piece together the complex puzzle of our universe's evolution. Section 7. Windows to the Universe. Probing extreme physics. Neutron stars serve as cosmic laboratories for studying extreme physics. The conditions inside a neutron star are so extreme that they cannot be replicated in any laboratory on Earth. This makes neutron stars ideal for testing our understanding of gravity, nuclear physics, and particle physics. For example, the intense gravity of neutron stars provides a testing ground for Einstein's theory of general relativity. The behavior of matter under such extreme gravity can be studied by observing the orbits of companion stars around neutron stars. Furthermore, the study of neutron stars can help us understand the properties of matter at extremely high densities. This knowledge could lead to breakthroughs in our understanding of the fundamental constituents of matter. Section 8. Cosmic Laboratories, Neutron Stars, and the Nature of Matter. Neutron stars offer a unique glimpse into the nature of matter. The extreme density of these objects pushes matter to its limits, creating conditions where particles interact in ways that we are only beginning to understand. Scientists believe that the interior of a neutron star may contain exotic forms of matter not found anywhere else in the universe. These forms of matter, such as quark matter and strange matter, could hold the key to unlocking new frontiers in physics. By studying the radiation emitted by neutron stars, astronomers can probe the conditions deep within these objects. This research could lead to a better understanding of the fundamental building blocks of matter and the forces that govern their behavior. Section 9. Conclusion. The enduring allure of neutron stars. Neutron stars are enigmatic objects that continue to fascinate astronomers and physicists alike. Their extreme properties challenge our understanding of the universe and provide a testing ground for our most fundamental theories. As we continue to study these cosmic lighthouses, we will undoubtedly make new and exciting discoveries. Neutron stars will continue to illuminate our understanding of the cosmos for generations to come. Their study promises to unlock some of the universe's most intriguing secrets, from the nature of gravity to the fundamental building blocks of matter.